It's time to get ready.
And lift off.
To blast off into space. As the sky at night is back, bringing you the very latest in celestial news and cosmic engineering. A lot has been happening since we've been off air. The Juno spacecraft made its closest approach to Io, Jupiter's moon, bringing spectacular images of its volcanically active surface. Incredible images also continue to come from JWST and the data it's sending back. 2024 is proving to be a wobbly year for moon exploration. Japan's SLIM mission landed on target despite being nose down, while the Odysseus robot also had a fall after landing, but marks the first private company to land on the moon. NASA also launched its Deep Space Optical Communications experiment, successfully sending back to Earth this recording of a cat chasing a laser. Its aim wasn't to share a cute cat video with passing aliens, but to test out the potential of faster and further communications by laser, instead of the traditional radio waves.
But the big news this month is that scientists have been sharing their initial findings from NASA's first asteroid sample return. So tonight, we're looking at Bennu, an asteroid that could, one day, hit our planet. If Bennu were to hit Earth, and that's a big if, it won't be for another 150 years or so relax for now. But just last year, NASA's OSIRIS-REx spacecraft returned to Earth with a piece of Bennu. Scientists from all over the world have been prodding and poking it, and now they're ready to announce their findings.
The Sky at Night team has been finding out what's been discovered now that the space rock has returned. Welcome to the Sky at Night.
In 2016, NASA's OSIRIS-REx spacecraft started its 1.2 billion mile journey to the near-Earth asteroid Bennu. Its aim? To extract some of the asteroid's material, which was then carefully sealed and returned to Earth. With 2 samples already obtained by the Japanese Space Agency, why is there so much interest in asteroids?
If you know one thing about asteroids, it's probably that dinosaurs didn't like them. When an asteroid hit our Earth 65 million years ago, just off the coast of what is now modern-day Mexico, it caused our planet's last great extinction. Good news in the long run for us descendants of scurrying mammals that survived the impact, but definitely bad news if you're a dinosaur. Astronomers weren't keen on asteroids for many years either. Sure, when they discovered the first few in the early 19th century, they celebrated them as new planets, but as the number mounted, they were quickly downgraded. Nowadays, we know of more than 500,000 of the things, so let's get to know them a little bit. First of all, asteroids are small, no more than a few hundred meters across, and they're rocky. Now, it is true that most of the asteroids that we've visited with spacecraft look more like potatoes than planets. But these are no small potatoes. Because the asteroids have been more or less unchanged as they formed billions of years ago. Look at this, tiny Dinakesh, visited by the Lucy spacecraft just at the end of last year. This is a place we went by accident, the equivalent of a cosmic motorway service station. We can learn more from larger worlds like Ceres and Vesta, both visited by the Dawn spacecraft. These are round, they're more planet than potato, and you can think of them as small proto-planets. They grew this big, and then things stopped. But where you're sitting 5 billion years ago would likely have looked very much like the asteroid belt does today. Rubble all over the place, and 20 to 30 worlds the size of Ceres or Vesta careening about, causing chaos. And it's from that chaos that our planet was formed. And even once the Earth was assembled, the asteroids were not done with us yet. Yes, they did for the dinosaurs, but billions of years earlier, they may have been beneficial. Could they have brought water to the parched surface of a dry early Earth? And who knows, they may have had a role in the origins of life.
With the potential to explain those big questions like how did life begin, Chris is heading to a place with samples that could reveal the answers.
The Natural History Museum in London is home to an incredible collection of rocks, from precious gems to unusual asteroids, and even samples brought back to Earth by the Apollo astronauts. But it's not just the displays that are fascinating. I'm off to meet two museum scientists who've been working on the Bennu sample return.
Hello. Hello.
Nice to see you both, and wonderful to be talking about the OSIRIS-REx mission, which sounds like a dinosaur in the collection, but it's of course NASA's asteroid mission. What was the mission trying to do?
Yeah, so OSIRIS-REx was NASA's first attempt to go to an asteroid, collect a piece of an asteroid, bring it back to Earth so we can study it here in the labs.
So Sarah, you've been involved in this mission for a long time. What was launch like?
Launch was amazing, yes, absolutely incredible. Cape Canaveral, everything went to plan, incredible experience.
And everything worked?
Everything worked.
Then you had this long 2-year journey to get to the asteroid Bennu. What happened when the spacecraft arrived?
When they got there, I think they were kind of expecting something a bit like a beach, lots of fine-grained material all over the surface. It turns out Bennu's surface was covered in these huge boulders, sort of tens of meters in size. Really interesting, really exciting, also a bit dangerous when you want to try and grab a sample off the surface.
So the plan was to go and scoop up some of the asteroid and bring it back, but the pictures of that happening look quite dramatic and exciting. Were you expecting this sort of reaction from the surface when you hit it?
As the sampling happened, the arm went down, and we were kind of expecting it would hit a kind of solid surface, but it just kept on going down and through as if it was just going into a ball pit.
And all of this dust came up.
All of this dust suddenly flew up, and it was only because of the thrust backwards that it actually managed to escape from Bennu, otherwise it may have sunk all the way through.
So this was designed as a sort of touch and go mission, but you disappeared into the asteroid.
Yes.
Good job the spacecraft survived. Sorry
Yeah.
about that.
No more to say to that.
You're like, yes, it was good. After a 7-year round trip, the spacecraft returned with over 120 grams of Bennu. The largest asteroid sample ever collected, with more than half of that trapped outside the container. OSIRIS-REx came back to Earth, sample landed, and Ashley, you were one of the first people to see it.
Yeah, I had an amazing experience. I actually was one of a handful of scientists who were there when that sample made it back to Earth. The Quick Look team is what we were called, or the Tiger team, waiting to get our hands on that sample and do exactly that, have a really quick look at what that material was.
And so what did you see? So you're in a clean room, presumably.
So the clean lab's really noisy. It's actually quite difficult to communicate, and so they want to keep it very calm, very quiet for all the curators to work with. And then the rest of us were just in a room next door to that, watching everything that was going on in that clean lab. And it was incredible. They took the lid off. We all jumped up, we did exactly that. We started pointing at things and going, that one's sparkly, that one's black. We're all geologists, so we immediately start thinking about what that could be telling us about the rocks.
But in the meantime, you had another challenge, which was getting into the sample collection jar itself, which proved a bit of a problem.
Yeah, what the curation team did, they turned their attention to the actual sample collection, the thing where all the material from the surface was going to be. And it's got 36 screws around it, and unfortunately 2 of those just wouldn't budge for them. So they couldn't immediately get all the material out of the sample collector.
It does sound frustrating that you've gone all the way to an asteroid and back, and you can't get the jam jar open, essentially. Was it a big problem?
Because it's in this curation facility, so you can't just put any spanner in there.
Right.
You have to have something that's been approved by NASA and is curation clean. It's not going to contaminate the sample.
Because this is stuff that hasn't been touched.
Exactly, yeah. So they had to go away, think about how they were going to do this, and they came up with a new type of spanner that they could use. And so they actually got it open about a month or so ago. So all the material is now out of the collector head.
Bennu samples have now been distributed to about 200 scientists around the world. And Sarah has a piece right here at the museum. So, are these the samples?
Yes, they are. They are. I know they look like really boring black spots.
Can I hold it?
Yes, you can.
This is a bit of Bennu.
That is a bit of Bennu, yes, brought back by OSIRIS-REx.
That's not boring at all.
No.
That's really exciting. So, It's this tiny grain here. It looks almost like a sand grain.
Yes, yes. So we received about a teaspoonful that was just grains about that size or
Okay.
even smaller. So
I'm
we
going to give
picked
this
up.
back to you. I actually
Yes.
feel quite nervous holding that. Yeah. So you
So-
pick that out of your teaspoon.
We've picked out these individual grains and CT scanned many of them, and then we've put them in epoxy and polished them like this.
Okay. And then you can place them in a microscope.
Yes, exactly. So this is the microscope I'm using today. So it's firing electrons down a gun here to the sample that's inside there. And this is an image of the sample of Bennu that I'm looking at.
So what can we see on the screen?
So what we can see on the screen is that most of the rock is really, really fine-grained, all the stuff around the outside. It's got bright bits here, which are an iron oxide magnetite. But most of the screen here is dominated by this sort of skeletal-looking grain, which is a mineral called olivine.
Which we see on Earth, right?
Exactly. It's a really common mineral on Earth.
And where would that have come from? Would it have formed with Bennu?
So it's formed before Bennu was around, in fact, before any asteroids or planets were around. And they give us a glimpse back into what the composition of our solar system was in these pre-planetary times.
So you expected olivine, but there have been some surprises as well.
Yes, so one of the surprises we saw as soon as we opened the sample return capsule, and that was, most of it was a black rock, which is what we were expecting, but there were little flecks of white stuff in there. And it turned out the white stuff was mostly a mineral called magnesium phosphate.
Each element in this map has been given a different colour, with the compound magnesium phosphate shown here as green.
So why is the magnesium phosphate important?
It's important because it's so abundant in Bennu, but it's not really abundant at all in any meteorites in our collection. It's an incredibly rare mineral. We don't really see it in Earth rocks at all, so it was just a complete surprise to see it. But we think it probably formed by the action of water. So it's probably telling us that in its early history, Bennu had loads of water that was creating all of these watery minerals.
Well, that's surprising, right? Bennu's
Yeah.
dry now. It's made of rock. It's not an
Yeah.
icy comet or something like that. So,
No.
so where's the water come from?
Yeah, so it probably means that Bennu formed in the outermost part of the solar system, and it formed with bits of ice grains incorporated into it that heated up and then became liquid.
So it's quite a complicated story.
It's an incredibly complicated story, and we're just at the beginning of starting to understand what it's telling us about the whole history of our solar system, from pre-planetary times to the origin of water and how that got potentially to the Earth.
I know you're a proper geologist, because the moment you say it's complicated, you light up and get excited.
Yeah, more complicated the better. There's so much in it, and each little grain is a little bit different from the others, so it's going to keep us busy for years and years.
Well, Sarah, thank you very much for showing us. It's genuinely exciting to be in the lab with Bennu, so thank you again.
Well, I'm really pleased to be able to show you, Chris.
Such small grains can tell us so much, but they're a challenge to analyse. How can it be done? Maggie's on the case to find out.
Today, I'm at one of the UK's most impressive science facilities, the Diamond Light Source in Oxfordshire. Right now, I'm standing above their X-ray synchrotron. Now, this huge machine is designed to look at some of the smallest objects in the world. It's effectively a high-tech, giant microscope. Scientists use the Diamond synchrotron for a huge variety of things, from looking at how viruses like COVID-19 work to figuring out which specific pigments were used to paint some of the most famous artworks in the world. This machine is also critical for analysing artefacts from space, including those new samples from the OSIRIS-REx mission. So I'm going to find out how it all works. I'm meeting Dr. Sharif Ahmed, one of Diamond's principal beamline scientists. Sharif, thank you so much for having us here.
Welcome to Diamond, Maggie.
I really want to get an understanding of how it all works, and I think this model can show us.
You're right, you're absolutely right. So essentially the synchrotron starts with electrons.
Electrons are released by heating up a metal. These are then sped up inside two machines. The first, a linear accelerator, and then a booster ring.
And in the booster ring, the electrons will go up to really up to about 98% of the speed of light.
So 98% of the speed of light. So how do you accelerate the electrons to get to that sort of speed?
We use radio waves in a particular frequency, and as the electrons pass through them, they essentially are pushed by these waves. And we keep doing that in a circle again and again and again.
The electrons are then injected into a larger storage ring. Once they have reached their optimum speeds, they move so quickly that they could travel around the entire world 7.5 times in just 1 second. And it's these high speeds that allow the groundbreaking science to happen at Diamond.
The storage ring is a multi-sided polygon, i.e. it's got lots of straight sections.
Okay, so it's shown as a circle here, but it's actually a series of flats.
Exactly, straight edges with something called a bending magnet that connect these straight edges. And every time we turn the electrons, we decelerate them.
Okay.
Because they have to slow. So it's very similar to how when you decelerate or brake your car, motion energy is converted into heat. So these electrons are very energetic. And as you bend them, they slow down. And that causes the emission of X-rays, ultraviolet rays, infrared, and even visible light.
You work on one of the beamlines.
Indeed.
And it's an X-ray beamline.
It is.
Can we see it in action?
Of course. Come with me. We can obviously go and have a look at it.
Fantastic, thank you.
Excellent. So all the X-rays are obviously coming through the ratchet wall.
The first room that the beam of X-rays enter is called the optics lab. Here, carefully aligned mirrors and precise filters allow Sharif to tailor the incredible powerful X-ray beam to the specific needs of each scientist. After that, it's onto the experimental hutch, where the X-rays meet the sample being analysed. And that's where the magic happens. Now, when we talk about X-rays here, are we talking about the sort of X-rays we get at the dentist or in the hospital, or are these different?
They are similar but different. They're much more energetic and powerful. A good comparison would be a laser pointer that you'd use for doing a presentation, for example, compared to a laser that's used for, say, melting or cutting metal.
The X-rays used by Sharif are 10 billion times brighter than the sun. And he's been using these to analyse the Bennu samples with Ashley from the Natural History Museum. And there's something special about this dyad beamline that takes their analysis to the next level. So what's dyad?
The most unique thing about this instrument is the fact that we have two X-ray beams, and it's done by these two detectors. So you have a very simple detector here, which is essentially an X-ray microscope. On the robot arm, we have something a lot more special. It's what's called a cadmium telluride direct detection system.
Using these two detectors, Sharif is able to combine images of the sample with data about the different atoms and molecules inside it to give insight that no other instrument can. So what does the data look like?
So I've got an example to show you very quickly. So what you're looking at here is, it's like a CT that you'd get at a hospital. So you can see a cross-section, or as if to cut an object. And over here, what you're looking at is, or the different materials in that particle. So that is from using X-ray imaging or X-ray CT. Yes. And this, the color image, is an overlay over that. So suddenly you can actually see the internal structure,
yes,
but also the material it's made up of.
And so you have been doing sort of samples from Bennu?
We have. We've had the pleasure of being the first synchrotron in the world, I believe, to have a Bennu sample. And hopefully at some point, we'll be able to show you images like this once we've gone through the process of reconstructing it.
Well, thank you so much. That's amazing. Just hearing the capabilities of this beamline is quite mind-boggling. And I can't wait to see the results from Bennu.
And the Sky at Night will no doubt be reporting on these results once they are released. Another scientist trying to uncover Bennu's secrets is Dr. Queenie Chan at Royal Holloway University. Queenie is remotely collaborating with a team in America and Japan where the sample is held. They're looking for small pockets of water trapped within the asteroid. George Dransfield went to talk to her about what this water can tell us and why learning what is contained within it is so important.
In your analysis then, what is it that you're actually looking for?
We are looking for tiny little bits of fluid inclusion within the samples.
Fluid inclusions, what are they then?
Well, fluid inclusions are little pockets of water trapped in a mineral as the mineral grow on the asteroid.
To find these pockets of water, Queenie looks at the minerals inside the asteroid sample under a microscope. The Bennu sample Queenie is working with is in Japan, and the images aren't ready to be released to the public yet, but she does have a meteorite sample in her lab that perfectly illustrates her work on Bennu.
We do have a salt crystal that's now sitting under that microscope.
Amazing.
And this salt crystal is coming from another sample, extraterrestrial sample from a meteorite.
It's alien salt.
It's alien salts, yes. Yeah, that's a mineral that's capable of trapping fluids as they grow. So imagine a glass, in your home that you put lots of salt, like really salty water in it.
Yeah.
And if you let it sit for a while, you start to see little crystals start to grow, little salt crystals, baby crystals start to grow, and bigger. As they grow, it's capable of trapping fluid within them. And this is exactly what's happening on an asteroid, and it's probably what's happening on Bennu as well.
Okay, so I can see the alien salt over here. Where's the liquid?
So you can see that alien salt staring at you now with those little black dots over there.
Yeah.
Those are the fluid inclusions.
The next stage is to analyse the water trapped inside the mineral in order to understand what's contained within it. Because not all water is the same.
Let's think about if you go in, take a glass, go into the river, get a scoop, and compare that glass of water to another glass of water that you take from the ocean.
Yeah.
The content is going to be completely different. You've got different kind of salinity in different water. The iron that's dissolved into the water is going to be completely different. The amount of organic constituents, for example, would be different as well.
Some scientists believe that the organic materials needed to start life could have been brought to Earth by asteroids. Queenie searches for these organic molecules using a process called spectroscopy.
So how are we actually going to be looking for organic molecules then in this sample?
With the Raman spectroscopic technique, we're capable of telling the kind of organic molecules we have in the sample. Roughly it tells us about the structure of the organics. We'll use other techniques subsequently. For example, another technique called TOF-SIMS, secondary ion mass spectrometry, is capable of telling us even more details as to the chemistry of it. We're looking at the little fragments that forms those larger molecules.
Amazing. So you're looking for the building blocks of the building blocks of potentially life.
Exactly, building blocks of the building blocks.
Nice.
Queenie and the international team hope that by analysing any tiny pockets of water trapped within the minerals on Bennu, they'll identify different molecules and discover if they are the ones that could have been key to starting life on Earth.
Today I've had my mind absolutely blown by alien salt and its ability to tell us something about the origins of life. Now, she does have quite a long way to go with this research, but I cannot wait to hear about the results as they come in.
The work scientists are doing on the Bennu sample could answer some big questions in the future. But in the meantime, our resident stargazer Pete Lawrence is looking up to the skies to tell us what can be seen this month.
Comets and asteroids can be fun to track and are a great target for amateur astronomers. But the first challenge is to identify them. And there's a quick and clever way to do this, which is known as the blink test. I did one recently for the bright asteroid Vesta, and the principles are quite simple. You record the stars in the field of view you believe the object to be in, like this one. And then, over subsequent nights, if you take another image and then you align the stars between those images and flick backwards and forwards between them, if you spot a moving object, that should be the comet or asteroid that you're after. If you head outside this month, there are two interesting comets which are relatively easy to locate. The first is C2021 S3 Pan-STARRS, which is an early morning object best seen from around 1 AM BST. To find it, locate the Northern Cross asterism in Cygnus the Swan. At the start of the month, it's located near the Coathanger cluster, Colander 399, slowly tracking up the vertical of the cross to end the month not far from the brightest star, Deneb, at the top of the cross. It may be a bit tricky to spot due to the myriad of faint background stars in the dense section of Milky Way found here. The blink technique will certainly help show its motion. If you're not a morning person, there's Comet 12P Pons Brooks, which could get bright enough to be seen with the naked eye. It has a 71-year orbit and will be closest to the Sun on the 21st of April. The evening twilight will make seeing the comet tricky towards the second half of the month, so probably the first half of April is the best time to catch it. To stand a chance of seeing it, you'll need a low, clear west-northwest to northwest horizon, and the use of binoculars is also recommended. Wait for the sky to darken sufficiently for mid-brightness stars to appear. The key markers for finding the comet are Hammel, the brightest star in Aries, Jupiter, the Pleiades, the star Aldebaran, and the Hyades Open Cluster. Aside from the comets, as ever, there's still plenty to see in the night sky, although it has to be said that the planets are rather sparse at the moment, too close to the Sun and lost in its glare. But there are still two which are worth looking out for. Jupiter is still there, low above the west-northwest horizon after sunset. It's been gradually catching up with Uranus over the past months, finally reaching conjunction when the pair appear closest on the 20th of April. They will be separated by just half a degree, that's the apparent size of the Moon, but the evening twilight will make the view harder to see. Meanwhile this month the Moon will be showing some interesting clair-obscur effects or tricks of the light. On the morning of the 16th of April, as it approaches setting, you should be able to see the popular lunar X and V. Effects which make the letters X and V appear on the terminator. That's the line dividing lunar night from day. On the evening of the 18th, the easy-to-see jeweled handle will be visible, an effect caused when the peaks of the curved Montes Jura mountain range catches the light of the lunar dawn. That's the viewing highlights for the UK, but the biggest event this month in North America happens not at night, but rather during the day. A total eclipse of the Sun. These rare occurrences are always a treat, so long as the weather is on your side, as we've found out throughout the years.
The Monty Umbi sailed from Liverpool a week before the eclipse with 300 members of the British Astronomical Association on board.
It's something I've wanted to see all my life, and all we can do now is wait and hope the weather holds.
We were all rather worried by the hazy conditions.
Oh, clouds, keep away, please.
I haven't given up hope yet. The moon has started to pulse onto the sun, and the great eclipse has started. And sadly, at the moment, from here on St Antony Head, we can't see it because the sky is totally overcast. It can clear dramatically at the last moment, and you never know.
There we go. Look at that. There's the diamond ring and the corona reaching out as the shadow hits us.
There's a break. Look there. There's a break in the cloud, and there is the crescent sun.
That is the most incredible sight. It really is.
This is incredible. The best corona I think I've ever seen in my life.
I can't believe this is over already. So diamond ring, get the glasses on.
By Jove, was it worth seeing?
Now, if you were lucky enough to see this month's eclipse in North America, and if the skies were clear, then do share your photos with us. You can do so via our Flickr account, details on the website at bbc.co.uk/skyatnight. We'll show a few of the best on next month's programme. But until next month, good night.
On BBC iPlayer now, a 3-part series exploring one of space exploration's greatest tragedies, the space shuttle that fell to Earth. For mind-bending conundrums such as, which is best, a bee or a wasp? Listen to The Infinite Monkey Cage, now on Sounds.